You can just get involved to explore our resources or donate to your Women Who Code program or expand your leadership skills. We also have a dedicated section for companies on global partnerships, and we also offer scholarships. Last but not the least, please don't forget to join our micro-content platform on Beacons, and the link is provided below. So here we are with our speaker, Nimrita Koul, and I would like to have a small introduction about our speaker. Nimrita Koul is an associate professor at Computer Science and Engineering. She holds a PhD in machine learning with a gold medal both in Bachelor of Engineering and Master of Technology in the Department of Computer Science and Engineering. She has an academic experience of 17 years with 7 years in research. Her research interests include machine learning and natural language processing. Nimrita is the principal investigator for the research projects in machine learning and natural language processing funded by Department of Science and Technology, Government of India. She has delivered multiple international workshops and seminars on data analysis, machine learning, and natural language processing. Nimrita Koul is also a senior member in IEEE and Association of Computing Machine. Here we are with the professor and handing it over to you.
Thank you, Kritika. And I'm really excited for today's session. And I am looking at many participants who were with us in the last session, and I hope this session adds value to your knowledge. All right, so I'm about to share the screen, but I can't share while other participant is sharing. Yes. Okay, just a second. I have shared my Jupyter Notebook Chrome window. Can you confirm? Yes, right? It's visible to everyone, right?
Yes, we can see.
Perfect. Great.
Thank you.
So, all right. I am about to start session 2, which is about text pre-processing and representation of text into numerical form for working with ML models. So before we dive into today's topic, I'm going to give a brief recap of what we have already covered in the previous session. We covered an introduction to NLP. We spoke about different tasks which we need to do as a part of NLP project, which included text pre-processing, tokenization, normalization, stemming, lemmatization, etc. Then converting words into numerical vectors. We also spoke about POS tagging, identifying named entities, relationships between words, and so on. We looked at various use cases of NLP like spam detection, machine translation, bots, and text summarization. We saw that the NLP has applications in fields like healthcare, finance, HR, etc. We spoke about 2 important libraries in Python which support NLP, that is NLTK and Spacy. We looked at the commands to download and install NLTK and Spacy. At the same time, we also briefly touched upon other libraries like Ginsem, Polyglot, and sklearn, which are there in Python that can be put to use for NLP projects. All right, in today's session, we are going to look at techniques for text pre-processing, which means basically bringing our data into a clean form, which is easy for ML models to work with. And then we will also look at different algorithms for converting text into numerical form so that ML models can work with them easily. Just a second, I'm so sorry. Yes. So, all right, text processing. To get started with text processing, I'll just give it a brief definition. Text processing means to clean your text data before you can apply further NLP pipeline to it. So the common tasks that are a part of text pre-processing are normalizing text, which means converting all the text into lowercase, then removing certain special words like stop words, most commonly occurring words, which do not add much meaning to the meaning of the text, then removing punctuation marks, removing special words like @ symbol or hashtags and tweets, Then we can do stemming, which means basically removing prefixes and suffixes of the text. Lemmatization, bringing the text into the root form or the form which is most commonly appearing in the dictionaries or thesaurus. Then correcting the spellings of your text, and then a little bit of exploratory analysis will be seen in this session, like plotting and all. We'll be using NLTK and Spacey, and in addition to that, we'll also use Ginsem for a spell correction and for a little bit of plotting. So what is the advantage of text processing? Definitely, text processing helps us in reducing the amount of text we feed into an ML model, which means dimensionality reduction. Some of us who are from an ML background understand the curse of dimensionality, which means as the number of columns or as the number of dimensions of your data increase, the models become very, very sparse, and usually the performance is poor. So dimensionality reduction means we just want to reduce the amount of text data we actually feed into an ML model, and hence we see performance gain because of this. For demonstrating various steps of text processing, I have used the coronavirus NLP tweets dataset from Kaggle. The link is available in this your Jupyter notebook also, and you can download the dataset, and henceforth we will see how to work with this dataset. As the first step, I have converted this data set into a pandas data frame. Now, for this session and for next few sessions, the familiarity with Python is assumed. I'm assuming that the participants are familiar with using Python and writing functions, handling data, converting data into a pandas data frame and things like that. So we are using pandas. We have imported pandas into this Jupyter notebook as PD. I'm using read_CSV function. corona_NLP_train is the name of my CSV file, which contains the data of tweets regarding coronavirus during 2019. After that, I'm just displaying first 5 rows of this data set. This data set contains columns like username, then screen name, location, what time it was tweeted, and what was the tweet content, and what was the sentiment of the tweet. There are 5 kinds of sentiments for these tweets: neutral, positive, negative, extremely positive, and extremely negative. So we are looking at just 5 rows of this data set. Some of you who are familiar with pandas know that functions like shape and columns help us to do a little bit of exploratory analysis of the data set. So data frame name dot shape shows us how many rows and columns our data frame has. So approximately 41,000 rows and 6 columns. Then what are the column names in our data set? Are there any columns, are there any rows which have null values or missing values? So we see that the location column has a lot of null values. We will drop all these null values using the function drop NA, and then again we check the shape of the data set. Now it's around 32,000 rows. So around 9,000 rows have been dropped which contained null values. Next, we are just dropping the columns which we are not interested in, columns like username, screen name, location, and the time at which it was tweeted. Remaining data frame has just 1 column, which is the original tweet. So from here onwards, we are starting the text pre-processing steps on this data frame, which now has just 1 column. The name of column or the heading of the column is original tweet, and it has the sentiment column. So here we can see first 5 rows of now data frame, which has 2 columns, original tweet and corresponding sentiment of the tweet. Now this is a pre-labeled data set where the sentiment is also available in the data set. In the next session, we will see how you actually can use this kind of data set, which has the labels available to train our own models for classifying tweets or for classifying movie reviews, for classifying text actually. All right, so the next step of pre-processing is to remove the stop words. Stop words are words like the, is, a, and, which occur very, very frequently in, I'm talking in the context of English text, which occur very frequently in our written or spoken text, and hence they do not add much to the meaning of the sentence. We can access the set of all stop words in English from NLTK libraries corpus called stop words. In this cell, we can see that we have imported NLTK, we have imported string. The string module has the built-in list of all punctuation marks in English, because we intend to remove both the stop words and punctuations in this cell. So I took all the stop words of English language in a variable called stop_words, and I took all the punctuation marks in English using string.punctuation in a list. combined the stop words and punctuation marks together in a variable called stopword and punctuations. And here in this line of code, we are using apply function and this code to remove all the stop words and functions from every row of the original tweets column of my data set, of my data frame. So train data is the name of data frame. We are trying to work on the original tweet column, and I'm trying to apply this thing to all the rows, which can be done using apply function. So here's my anonymous lambda function, which is trying to join together all the words in the tweet if those words do not fall in the stop words or in punctuation marks. So basically, we are stripping all the tweets of the stop words and the punctuation marks. And then I'm just printing out that original tweets column of the data frame. Here you can see that the words like the, is, a, and, etc., which are stop words, have been removed. And at the same time, the punctuation marks also have been removed. Then in this cell where since we are working with the tweets data set, a lot of URLs, a lot of mentions and hashtags will be there. So we will be removing them also. Removing the URL, for removing URLs, we are using regular expression module of Python, RE module of Python. So I have composed a pattern here, which matches all the URLs generally consist of 3 groups of text, a www dot followed by something dot followed by something. So this is the pattern which matches a URL, and we are removing all the URLs from the tweet we pass to it. Again, after composing this function called remove_URL, I am applying this function to every row in the train data original tweet column. So this is the apply function, which applies the function name you pass to it to every row of the data frame. So here is the data frame. After applying this remove URL function, all the URLs have been stripped out, have been removed. For example, here we can see there's a URL appearing in row 0. And here we can see that this URL no longer is present. The next step of pre-processing is to remove hashtags and mentions from our tweets. So again, we have composed a function here, remove mentions and hashes. You pass it a variable of kind text, and then we use again the regular expression module, compose a pattern which matches all the mentions which start with @ sign, and another pattern which matches all hashtags which start with hash symbol. So after removing all of them, we return the tweet. That means after stripping off the text of the tweet of all the hashtags and all the mentions, we are returning the tweet. And once this function is composed, we use the apply function to apply this to every row of the data frame's original tweet column. What we get after applying this is the text which does not contain any hashtags and any URLs and any stop words, any punctuation marks, all of that. Now, because of this, we can see that this first row has become empty, right? Perhaps it contained only the hashtags and URLs. So we stripped the data of that. So this row is completely empty now. We used to handle this also. We'll handle it in a moment. Next, we are writing a function here to remove all the emojis from the tweets. This function, remove emojis, again uses a regular expression, and I have specified some patterns. These patterns match the emojis. We are just replacing them by an empty string. Then, after composing this function, like above, we use an apply method to apply this remove emojis function to every row of my original data frame. So here we see the emojis also have been dropped. Here's a small demo of how this works. I have specified some text here. This text contains the Unicode representation of 2 emojis. I'm just printing the text as it is. And then I have applied the remove emojis function to this text. We'll see the output of both these print statements. Here is your the original text. These are some emojis. And here is a scissor and something. Right, 2 emojis. And here are here's the output after removing the emojis. So basically what this function is doing, it is identifying all the emoticons and emojis, those symbols which are used to represent sentiments sometimes, and then it is replacing them by empty strings. Next, we are removing any characters which are non-ASCII by the corresponding ASCII representations. For doing this, for removing non-ASCII characters, we will use a module in Python, which is called Unicode Data. In Unicode Data module, there's a normalize function. You specify what kind of replacement you can do. So we will be using NKFD format to remove all the non-SKY characters and basically replace them with a composition of SKY characters, right? So after this function is written, we again use the apply function to apply this function to all the rows of my data frame's original tweet column. Right, next we are about to handle this empty row and any other empty rows which may have been produced because of above preprocessing. For that, we have created again a function called empty strings. I'm using the regular expression pattern in this case also, therefore this module RE is coming into picture again and again. We are applying a pattern which consists of spaces or one or more spaces, and then we are using the replaced pattern nan to replace all empty spaces with a special word called nan. After this function is written, we are using apply function again to apply it to every row in the data frame. We composed many functions for preprocessing, and for all those functions, we saw this pattern of using apply function. Apply function basically is a vectorizer, which allows you to apply same function to all the rows of the data frame without using a for loop or without doing things again and again manually. And then once we have replaced all the empty strings with this special text nan, we are using this line of code here, which drops all the rows, which drops all the tweets from our data set, which contain a nan. The resulting data set now is consisting of original tweets and sentiments. None of these tweets contain stop words. None of these tweets contain special non-SKY characters. None of these contain punctuation marks or emojis or hashtags or mentions or URLs. Right, so this is the data set we are going to now use for further processing. Next, I am going to demonstrate spell correction using GenSem library. Now, this correct function, which appears in the GenSem library, takes a relatively good amount of time for applying to 32,000 rows of a data set. So for demonstration purposes only, I have extracted a small subset of tweets, a small subset of rows from the original data set, first 10 rows. And we are applying this spell corrector function only on these test rows. It's only for the purpose of demonstrating it quickly within time. Otherwise, for 32,000 rows, it takes around 3 to 4 minutes to work on the data, depending on what kind of configuration you are working on your computer or your laptop. So this is from a TextPlob library. The TextPlob library provides us a function called correct. We are using that correct function from TextPlob library and applying this correct function to every row of the data set which contains original tweets. In this case, this smaller train data has just 10 rows. So this quickly worked out, and I am now having the original tweets column and the sentiment, and a new column is added to the data set where the spellings of all the words have been corrected. If there had been any spelling mistakes, they would have been corrected automatically.
Sorry to interrupt, Nimrita. By this time,
Yes.
before we get into
Yes.
the next session,
Yes.
we have a few questions which needs to be
Sure.
answered.
Sure.
There is a question from Maya. She asks about dropping the null values of location, the column
Yes.
location. So
Yes.
she's asking, why not the location column and other columns before checking for null values needs to be dropped? If you're
Since,
not,
yes.
Yeah.
See, our purpose here is to demonstrate text preprocessing, right? So the columns like username, screen name, location, the first thing is that there are a lot of null values in location. And the second thing is that these columns are not predominantly text columns, right? They are numbers. So we just drop them. Either you can drop all the columns which are numerical because we don't want to work with them during this session, right? We are demonstrating text preprocessing here, and they are not text. The other thing is, in case you want to retain the location column, we just drop the nan values. That will also work equally well. In case you need to plot, or in case you need to analyze what tweets are coming from which particular location of the world, or if your project deals with geographical based classification of tweets, something like that. In that case, you might want to retain the location column also. But in this project, in this session, my focus was on demonstrating text pre-processing. So we just dropped the location. But definitely, if you're working on a project, which is, for example, classifying tweets based on geographical location, then you need to retain the location column also. And for handling all the NaN values, we simply drop the NaN values or replace them with the value of a location, which is most commonly occurring, for example, mode of that column. Or we can apply some kind of label encoding or one-hot vector encoding at the later stage. We'll see that also. If you have a column which is categorical and you need to convert it into a number, how to handle that column. Does that answer your question, Maya?
I think she is quite not convinced. She is asking, like, we drop many rows who only have missing values in the location. So there is a loss of information when there doesn't need to be.
That's right. This depends on your project, right? What column is informative for you and what column is not informative for you. For example, in the project in next session, when we are working with the data where this location column also needs to be retained, we will retain it. But now the focus is on demonstrating text pre-processing, and this location column does not have a lot of text. Do you get my point? Yes, this is primarily one word, right? One word, just the name of the location. Yes, and when we are working on an actual project where we are doing analysis, for example, geographical analysis, in that case, we will definitely retain it. Okay, Maya is still not convinced, right?
Yes. We'll take this at the end of the session. Maybe we'll move to the next question.
Yes, we'll take it at the end of the session. And we'll also do what she's saying in the next session when we are doing a project on NLP, a full text classification project.
Yeah, that would be great, Maya.
Yes.
Yes. Professor, there is one more question, like, wouldn't emojis be an important piece to tag the sentiment?
Yes, they will be important when we are doing sentiment analysis. But right now, the focus is only on pre-processing.
Okay. So why do we do train and test the data when we already have label data?
Again, we are getting confused here. The question is coming from the frame of reference where they are thinking about a text classification or sentiment analysis project. But the focus of this session is only on text pre-processing techniques. How to pre-process your text, how to drop something which you're not interested in. In this case, it is that we are dropping emojis, but there may be special characters in your text which are not meaningful, which are not useful. You may be able to drop those characters also using the same code, using the same logic of a regular expression.
I think we
right.
move.
So
I think we move to the session, Professor. Yeah.
Yes. Yeah. So next time when we are doing the project, we will see what exactly are the informative columns. What are the words which we should retain? What are the symbols which we should retain? This session only on text preprocessing. For any project, what are the general steps of text preprocessing that we need to use? Is that okay? At the end of this session, we are not using the data to classify or to identify the sentiment. We are only demonstrating pre-processing that needs to be done on text data of any kind. And by removing the emojis here, we are trying to demonstrate how to remove certain symbols. We'll come back to this at the end, right? Shall we move on?
Yes, Professor, please.
Yes, right. So next, after our text data is now free of all the words that may not be very informative, we'll move on and we'll look at the NLP steps of tokenization, stemming, and lemmatization, and so on. So tokenization is the task of breaking your text in the which may be in the form of a list or in the form of a string into individual words and symbols of punctuation. NLTK library provides a built-in tokenizer. It provides a function called word tokenize, which you can import from NLTK library, and a special function called white space tokenizer can be used to split your text into individual words, which are called as tokens also. So for this, again, we have written a function called tokenize. this tokenizer function and this tokenized function can be passed a piece of text, and it will just split it into individual words and return the list of words to you. So just like above, we have used apply function and applied this tokenized function to every row of the data set of our data frame. Here is every row of my text. Now you can see that instead of it being a single sentence, it's a list containing different words of that sentence. This is the meaning of tokenization. So from a continuous list or a continuous string, it now looks like a list of separate words or tokens. The next step of preprocessing we apply to this data set is lemmatization. Lemmatization means, as I said, to bring the word into a form which is commonly found in the dictionary, a valid word which is found in the dictionary, a root word corresponding to a word. For example, the words like ran, runs, running, all of them, for all of them, the root word is run. So lemma for these words is run. Lemmatizer does exactly that. We are again using here the lemmatizer from NLTK library. The name of lemmatizer is WordNet lemmatizer. And we are applying this lemmatizer to every row in our data set, again by composing a function first and then using apply function to apply lemmatization to every record, every row in our data frame. The next step we apply is stemming. Stemming means basically to strip off the prefixes and suffixes from the words. Here is something I would like to say. Stemming and lemmatization may appear, the results of stemming and lemmatization may appear similar, but there's a difference. Lemmatization essentially gives you a word which is a valid word in that language, and stemming may not sometimes give you a valid word. It just strips off the suffixes, which sometimes may result in a word which is not a valid word. So we applied lemmatization and then we applied stemming on all the rows of our data set. Next, we are going to find out what are the unique values of sentiment. That can be done just by applying the unique function and a bit of plotting. Next, we will see what are the most commonly occurring words in the tweets and what is the frequency of those words. For this, we are using two Python modules, iter tools and collections. Combined all the records, all the rows of the data set into a list. This list is called all tweets. And then we combine together all the words of these lists into a variable called all tokens. And then we are counting the frequency of all tokens. So I'm just printing here the top 10 words which are used in these tweets. The first word is price, which has been quoted, which has been used 5,700 times around. The next word is store, grocery, food, supermarket, COVID-19, consumer maybe, and people and shop and go. So we can see that during those times, shopping and stocking up their necessities was on top of people's minds a lot. And then we are plotting these words in the form of a bar plot using matplotlib Python library. Here is what the plot looks like. This is the price word, which has highest frequency, 5,700 around, then the word store, then the word grocery, and so on. Next, we are going to see the demonstration of scattertext library of Python. Scattertext is an excellent tool if you wish to categorize, if you wish to analyze what are different types of sentiment in your data, or what are the different characteristics of your text corpora. So for that, you need to first install scattertext. If you are installing directly from Jupyter Notebook, use pip install scattertext. In case of Jupyter Notebook, you need to append an exclamation mark. If you're installing at the Python prompt, just go with pip install scattertext. Once it's installed, you can directly call it on your data set, or you might want to extract some portion of your data set on which you want to apply the scattertext. In this case, I have extracted only those rows from my data set where the sentiment is negative or the sentiment is positive. So we are not looking at extremely positive, extremely negative, or neutral sentiment. We are looking at negative sentiment and positive sentiment only. So here is the data set which contains tweets corresponding to positive sentiment value and negative sentiment value. And here is what we have done. We have combined all these tweets together in a single list, and then we have passed them through Spacy. We spoke about Spacy in the last session. Spacy has built-in support for around 42 languages. It has ready-made natural language processing pipelines, pre-trained pipelines for those languages. These pipelines come in different sizes, small, medium, and large, which means essentially how many words do they cover, what do they provide about the word? What additional information do they provide about the words? For example, the pre-trained pipeline, en underscore core underscore web underscore sm is a small pipeline of English language, which contains words and their POS tags. POS tags means part of speech tags. What is the grammatical class of the word? It also contains information about named entities in English text. It also has information about stop words and all belonging to English language. It is a smaller library, a smaller pre-trained module. Then we will see later in the session today, there is also a large module which has word vectors also corresponding to English language words. So in this cell, I have imported Spacey and I have loaded this small language of small model of English language. Then I am using this NLP object to parse all the tweets of my in my data frame. By applying this NLP object to the text of the tweet, we basically are converting it into an NLP representation or Spacey's internal object representation, which will have not just the word, but also additional information or annotations of those words. After we have composed this parse tweets function, just like above, I will use apply such that this parse tweets function is automatically applied to every row in my data set. So this data set is data set which is applied on by the parse tweet function is now returned in a new column of the data frame called parsed. So this was what my original data looked like, just individual words. And this is what they look like after they have been passed through Spacey's NLP pipeline. So this is a tuple which contains words. It looks like just words, but internally they also have the additional annotations with them. Next, we are using the scatter text module to actually plot. So we have to import scatter text. You also have to import from IPython, the iframe display and HTML, which are used to create an interactive display for you here in the output cell of the Jupyter notebook. We just look at this output. This is very, very interactive display. You can see all the words of your corpus of your data frame, and they are color coded. The words which have negative sentiment or which have very positive sentiment are appearing in different colors, blue and red. And then there are some words appearing in orange color. When you point your mouse there, you will see the details about that word. The word is everyone. It appears 57 to 68 per 25K words, and it has some score corresponding to it also. You can search in this graph for a specific word. For example, I can search for the word list and it shows me the details about the tweets which contain this word and what was the frequency of this word in negative tweets, what was the frequency of this word in positive tweets. So an excellent way for you to analyze your data set, depending on two groups here, positive and negative. You can do this with any two groups, for example, extremely negative and negative, or neutral and negative, and things like that. So a way of analyzing your data set before deciding what to do further with them. So here we see some words which appear in negative tweets most commonly: panic, panic buy, empty, stop, people, essentials, perhaps, toilet, shelf, and all that. And then we see words which appear in positive tweets most commonly: stay, pandemic, are, thank, Amazon, and so on. So this is scatter text module of Python. We are going to look at now text representation. Should we take some more questions here, because we are moving to our second kind of text analysis next?
We do not have questions pertaining to this section, Professor, so that we are good to move forward.
Yeah, great. So next thing that we are going to look at is representation of text, which means the text that we speak or whatever we write is in the form of alphabets, A, B, C, D, or alphabets of a specific language. And your ML models, which essentially include a lot of matrix multiplication, cannot work with this kind of data. So there has to be a mechanism of converting this representation of alphabets into numerical form. The most common representation of these alphabets or the words or the sentences in the form of word vectors of numerical values, the vectors of floating point values. And every text document or every text corpus is represented as a multidimensional vector space, which means if a sentence has 10 words, then there will be a vector space which has 10 vectors. Every word corresponds to one vector in that space. So before going ahead, we'll talk about a little bit of terminology. In NLP, a document is a collection of words. For example, a notepad file or a file in front of you, a collection of words is called a document. Vocabulary is a set of unique words in that document. Unique, by unique, I mean that we just do not consider words repeatedly. And the token is one word or basic unit of that data, one word or even a punctuation mark. And what is a corpus? Corpus is a collection of documents, which means a corpus is a set of documents. And the context of a word means or refers to the words which surround a particular word. I love a rose, or I love pizza. So I and love are the words which form the context of the word pizza. And then the vector embedding. Vector embedding means a technique of creating numerical vectors from the text, or the vector you created, that itself is also known as a vector embedding. So there are multiple ways in which there are multiple algorithms in which the words are converted into vector embeddings. And all of these embeddings must follow certain properties, right? One important property and most essential property is that it should be able to identify, it should be able to represent every word uniquely. And then this representation should also be able to capture the similarity in certain words. For example, cold coffee, these words are often found together. So the corresponding embedding or the corresponding vector representation has also been somehow able to capture this closeness, or they're occurring together very frequently. Then we should be able to perform arithmetic operations on them. For example, we should be able to determine mathematically the similarity between words or the distance between the words. We should be able to identify synonyms or antonyms from the vector representations of the words. And then whatever computing we are doing, whatever analysis we do on the text, there should be some way of doing that analysis on their corresponding numerical representations also. And another very important feature of an embedding is that once you have a numerical representation of a word or a sentence, it should be possible for us to map back to the sentence from the embedding and easily compute that embedding from the word itself. There are some 7 techniques which are used, and we will see all of them. One-hot encoding, the basic one, the primitive one. Then we have bag of models approach. We have TF-IDF approach to vector encoding. We have word-to-vec, glove, and fast text, which are commonly used techniques. And lately, after 2015, we have transformers, which use their own very dynamic embeddings for the text. Looking at one-hot encoding first, this is a very simple technique. If you have a sentence with a set of words, for example, I have 4 words here, apple, banana, orange, and mango in a sentence, we use a numerical vector. Numerical vector means a binary vector in this case, which consists only of zeros and ones, and we use only one in every vector, which means every binary vector will have a 1 at one place. The word represented by another vector will have 1 at a different place. Apple, for example, we represent by 1, 0, 0, 0, banana by 0, 1, 0, 0, orange by 0, 0, 1, 0, and mango by 0, 0, 0, 1. So this is a 4-digit binary vector, and every unique word has a 1 at a different position in the vector. These 4 vectors represent these 4 words in this document, which has only 4 words. If my document has, for example, 1000 words, we will have 1000 vectors, and every vector will be 1000 digits long. And this will be a huge vector space to represent just the 1000 words, and it will scale up in proportion to the number of words in your document. This is exactly because of this reason that one-hot encoding is not used any longer for the models like BERT and transformers. For any real-world NLP models, one-hot encoding is not used because of its huge dimensionality side. And all of these vectors are sparse, which means there is 1 only in one position and rest everything is 0. Anyway, we'll see how to implement it in sklearn library. In the pre-processing module, there is one hot encoder class which can be imported, and we will see how it's used to encode the text into a numerical format. So we have a piece of text which is called the variable document. The rose is red, the violet is blue. This is simple string of text. I've split this into a list, and then I have split that list into tokens also. And for every token inside this list, I'm computing word ID. Word ID means simply the word and a corresponding number given to that word. And then for every word ID, I'm computing their token IDs, which essentially is a number corresponding to every token in the sentence we have above. So this is the document. These are the tokens, the individual words within the document, and these are the word IDs. We can see that every unique word in this document is given a number, is assigned a number. These are decimal numbers, 0, 1, 2, 3, 4, and 5, right? And these are the token IDs. By token IDs, I mean, if we need to reconstruct this sentence from the numbers we have given to them, then see, first number is of 2. The 2 is the number of the 1 is the number given to rose. So the rose, 0 is 0 refers to the word is. The rose is 4 is the number of word red. Rose is red. Again, the 5 is the 5 refers to the word violet. The violet is then blue. So this is the code, the numerical code, which reconstructs this sentence for you based on the numbers we have generated for every word in this sentence. This is exactly what one-hot encoder does. We create the object of one-hot encoder class, and then we use to fit it to our data, to our token IDs. And here is the vector we get corresponding to all the words in the sentence. This vector corresponds to the word the. This word corresponds to the word rose. This corresponds to next word. And for every word, for example, if we had 1, 2, 3, 4, 8 words in our sentence, we have 8 words, 8 vectors corresponding to every word in the sentence. We observe that these are sparse vectors and these are binary. Every vector has one only at one position, one unique position, and every vector uniquely identifies a word in this document, where I already said a document is just a set of words, a set of tokens. This is one-hot encoder, not used much because of high dimensionality. Then we have a bag of words representation. Bag of word representation considers a set of words or a document just as a bag of words, where it gives you a numerical representation of the words, but it does not talk about the relative order or the position of the word in that document. We'll see an example here. Here's a document 1. Document means the piece of text. John likes to watch movies and Mary likes movies too. These examples I have taken from the Wikipedia page of Bag of Words model. There is another piece of text which says Mary also likes to watch football games. So these two sentences, for these two sentences, your bag of word model will first compute the vocabulary. Vocabulary means the set of unique words in your text. So John likes to watch movies. These are the vocabulary. These are the words in your sentence 1. This is vocabulary for sentence 2. Mary also likes to, and so on. And then this is the bag of words, which represents the document 1 with vocabulary 1. So John appears 1 time. Like appears 2 times. There are 2 likes in first sentence. John likes to watch movie. Mary likes movies too. So the word like appears 2 times. Here in the bag of words model, you have the frequency 2 given to the word likes. The word 2 appears 1 time. Watch appears 1 time. Movies appears 2 times, and so on. So what we see in the bag of words representation of a first sentence or document 1 is that there's a word and there's the frequency with which that word occurs in the document. There's no information about what is the relative order or which word is occurring after the previous word, and so on. So this bag of words model does fine for a lot of tasks, but it is insufficient for the tasks where you need to predict the next word, for example, where you need to generate NLP, natural language. And we'll see that this bag of words model works pretty well if we are combining 2 documents. For example, here's a third sentence, which is formed by combining sentence 1 and sentence 2 together. John likes to watch movies. Mary likes movies too. And the second part, Mary also likes to watch football games. This sentence is a combination or a union of previous two sentences, document 1 and document 2. And its corresponding bag of words model contains the names of all the words and their frequency. So we see John appears only 1 time, likes now appears 3 times, 2 appears 2 times, and so on. So this is simple bag of words representation, which takes into account a document, its vocabulary, and the frequency of words in that document, with no information about their order or no information about their position in the document. So here we have the code for applying this bag of word model. Before that, there's a small function which I have written to pre-process the text, just in order to demonstrate that.
Sorry to interrupt here.
Yes.
We have few questions pertaining to this
Yes.
topic. So one is from
Yes.
Jennifer. She's asking, are word IDs applied at random? Just confirming that it's not identifying where the word is placed in a sentence.
This word ID, right? This is not the word ID. It is the frequency of the word. Is the question regarding bag of words model or regarding one-hot encoding?
Okay, there is one more question regarding one-hot encoding. We will take it later.
Okay.
Jennifer
Right.
asked, are word IDs applied at random? She just want to confirm that it's not identifying whether the word is placed in a sentence.
In one-hot encoding, the word IDs that we printed are generated at random. In
So
bag of words model, there are no word IDs.
There is one more question pertaining to one-hot encoding. What is the max number of words you would recommend for one-hot encoding and vectors?
For a small data set, there's no hard and fast rule. But for small data set, which has, let us say, maximum 100 rows, you can use one-hot encoding. That also depends upon what kind of categorical data is this. If this is ordinal data, then you can go ahead with one-hot encoding. Then you should go ahead with label encoding instead. And if it's unordinal data, that means there is no inherent order in your data, then only we should go for one-hot encoding. Again, for small data sets, not more than 1,000 rows, for example.
So,
if it's beyond 1,000 rows, then we go for embeddings like word to vector and glove or fast text, as we will see ahead.
There is a request to provide examples where each one of these vectorization methods can be used or should be used.
Sure, we'll speak about that.
Yeah.
A general guideline is that when your data has a lot of rows, when your data set has a lot of rows, do not go for one-hot vector encoding, because one-hot vector encoding adds that many columns to your data frame. It increases the dimensionality tremendously. Right? And yes.
There is one more question from Kamshal. Do we have to process text before doing sentiment analysis of reviews with BERT?
Yes.
Correct.
Yes. A lot of text pre-processing, like lowercasing and removing stop words and removing punctuations, is built into these models, right? Which convert your text into numerical representation. And some pre-processing you may still need to do, depending upon your task-specific project.
So this question is like pertaining to the topic that we discussed earlier. If we were creating a ticket management system to tag ticket descriptions to many different work types, we will be following the same method for cleaning the data. Is that right?
Yes. You will look at exactly what contents are there in the ticket's description, right? You may see that there are certain symbols which are occurring. You may see that there are a lot of people who have not given some information. So missing values are there, specific symbols are there. By doing that analysis, you have to figure out what kind of data pre-processing you need to apply. There are no answers which apply to everybody. There's no one size fits all approach to this thing. But the steps like removing stop words or doing lowercasing, they apply to almost all the NLP projects. And rest, like what special symbols you want to remove, and what else you want to do, whether there are a lot of URLs, do you want to retain those URLs, do you want to drop them? That depends on your specific NLP task.
There is one more question. How do you know to change non-ASIC to ASIC? Yeah.
Non-ASCII characters means characters, some characters with accent over them. which generally we do not want to process, or which we are not interested in while we are working with English language. The characters which appear in languages which are non-English, we just drop them. And that can be done using the Unicode module, which is a built-in module in Python. It has the built-in support for you to handle those non-ASCII characters or convert them, replace them with corresponding composite characters from ASCII.
The attendee also wants to know about the positives and negatives of applying this method.
For removing non-ASCII characters, are you asking about the positives of removing non-ASCII characters?
Yes.
Yeah. So suppose I am working with tweets, and my whole focus is on analyzing the content of English tweets. And in between there are people from, let's say, a different language and who have used specific characters. And in general, my 90% of my data set is in English. So I may not want to focus on that kind of special symbol or special this thing in my data set. One way is to just drop it. Another way is to replace it by something which appears in English also. It's a way of normalizing your text, bringing it into a consistent format.
I think that is all for now. Professor will proceed.
Yes. So again, I'm telling there's no straight answer, like this should be done and this should not be done. It depends on what is your data looking like and what is your ultimate aim to do with that data. What exactly is the task you are dealing with? So one hot encoding, we are looking at the vectors where one vector corresponds to every word in your document, and this vector has the digits which is equal to the number of words in your document, and it is a sparse vector, which means there is a positive value only in one of the places, rest everything is 0. Bagsoft model has a word and the corresponding frequency of the word. It does not specify you where does that word occur in the sentence. So for using bag of word model, we'll first apply a bit of data preprocessing. We have seen it above already. In this function, I have combined a lot of preprocessing steps in a single function. We imported certain required libraries of Python and NumPy, regular expression, string, Unicode data, then stopwords from English, nltk.corpus, then lemmatizer, then we are building an object of lemmatizer in the process text function. First, I am removing the non-ASCII characters, right? This is using Unicode data's normalize function. I'm telling it what kind of normalization I want to apply to this text. For example, I'm ignoring anything which is non-ASCII. I'm dropping anything which is non-ASCII. Then I am substituting everything which is a capital with a small case. Then I am making translation, replacing every punctuation mark with an empty string. Again, this text.translate function helps us to apply a function to every word you pass to the text. So this make trans takes 2 parameters. What do you want to replace and where do you want to replace it with? So we are trying to replace all the punctuation marks with empty. We are removing all the punctuation marks. We are converting all the text into lowercase here. And then we are removing all the stop words using this code. We are dropping every word which is a stop word. We are dropping all the words and then all the words which are stop words, and then we are lemmatizing the remaining words. So many steps of text preprocessing, which we saw above separately, now I have combined together in this process text function. So by applying this function, all these steps of preprocessing will be applied to the data set. For demonstrating bag of words model, I have used the count vectorizer class from sklearn's feature extraction module. Again, we will demonstrate it as a data frame. So pandas is required, imported NLTK. Here's the document. Document means here's my text. The rose is red, the violet is blue. A simple text for demonstration purpose only. Now this as well maybe 1 million rows of your data frame containing the text. For demonstration purpose only, we have taken a very small piece of text so that we can see what is happening, what output is generating out of it. So for this text, for every item of this, for every element in this text, I'm applying the process text function. Process text function does this, right? It removes the non-ASCIIs, does the removal of stop words and so on. And for every one of these words, then we are dropping the empty strings also. And then we are building a count vectorizer class, which is BOW count vectorizer bag of words model. You pass different parameters to these classes. For example, say here we have used just 2 parameters, mindf and maxdf. MinDF requires mentions how many maximum documents, how many minimum documents should the word occur in for it to be represented using the BOW model. So MinDF is equal to 0 means the document, at least 0% documents should have that word, which essentially means that the word should be present at least once in the corpus. And maxDF is equal to 1.0, which means maximum it should be present in 100% of the documents. Here's a catch about the parameter we pass to count vectorizer. It can be an integer or it can be a floating point value. If you just look closely, this is 0 point, which means it's a floating point value. That means we are considering the percentage of documents to look at. Your text should be present, your word should be present in a minimum of 0% documents, which means even one occurrence of the word will be considered for converting it into a vector form. And max is equal to 1.0, which means the maximum word can occur in 100% of the documents. It essentially captures even one occurrence of the word. And then once we have created the object of this class, we are using it to fit to our data. That fitting is done using the fit transform function. We are passing it our process document. Process document is a document we have after applying process test function to it and removing the blank spaces from it. This results in a matrix, which matrix is represented in the form of a compressed sparse row format. We'll see what that means in a minute. And here is the vocabulary of my text. If you remember, vocabulary means all the unique words after dropping stop words and punctuation marks. So this text here, the rose is red, the violet is blue, has these words finally as its vocabulary without the stop words, the, is, and so on. So here is its corresponding numerical representation. This representation is known as compressed sparse row format, which means it tells you the row number and it tells you the column number where the value is 1. In row number 0, the value is 1 in column number 2. In row number 1, the value is 1 in column number 1. In row number 3, the value is 1 in column number 3. In row number 3, the value is 1 in column number 0. So this essentially is also somewhat like the one-hot vector encoded, but it is stored, occupying very small amount of RAM in the computer. So here's what the compressed sparse row format looks like. This is your data, which correspond where one row corresponds to a one vector or one word in your sentence. And this is what the representation is like. It has data, which is 1 here, 2 here, and -1 here in third column of row 1. Then we have 6.6 here in the fourth row, and we have 1.4 here in the final column of the fourth row. Here are the indices corresponding to the columns, which column contains 1, which column contains this. And here are the row numbers. Row number 0 in column number 1 contains a 1.0. Row number 1 in column number 1 contains a 2.0. Row number 3 in column number 0 contains a 6.6. Row number 3 in column number 4 contains a 1.4. So this is storing the matrix, but using a lot less RAM. If you wish to see the expanded form of this, we can just use a toDense function. And here it shows us the expanded form of the vectors corresponding to the words in your vocabulary. This word corresponds to the word blue, this corresponds to the word red, this corresponds to the word rose, and this corresponds to the word violet. So essentially what we have achieved is a numerical representation of our data where it tells us what is the corresponding vector without telling us that what word occurs at what position in the original sentence. No relative ordering information is preserved. This shortcoming is overcome to a small extent in another bag of words representation or another model of bag of words, which is called a skipgram or n-gram model. N-gram model also records only the frequency, but it can record frequency not just of individual words, but of n-grams, which means it can record the frequency of groups of words together. I can look at 2 words at a time, which is called as bigrams, and I can record the frequency of those bigrams. How many times does, I like occur in a sentence? I and like are 2 words, 2 grams. Similarly, it can record the occurrence of triplets or trigrams. How many times the triplets of words occur in a sentence? So this is a way of bag of words n-gram model to store not just the frequency, but also the words which occur together in a way of relative context of the words is the information regarding relative context of the words is also stored in bag of words representation with n-grams model. For creating this representation, we again use the count vectorization class of the sklearn libraries feature extraction module. Same way like above, I have defined some text here. This text consists of 3 sentences. The rose is red, the violet is blue. This is some text just for demonstration. And then we have fit the count vectorizer model, again like above, but this time the arguments are different. We are specifying n-gram range. N-gram range makes it different from the model we used above in simple bag of words model. This time it is an n-gram model, which means it will look at 2 words at a time. And it will consider the frequency of this pair of words or bigrams at a time. And we can specify it, what words to remove by specifying stop_words parameter, which essentially means we are telling it what kinds of words are stop words. So there, in this case, it is English words, which are stop words, which the model should automatically draw. And then we pass it the document for fitting using fit transform function. And then we tell it to give us the names of features, what features or important words it identified. And then we can print the matrix. Matrix essentially means the set of vectors, the set of numerical vectors it has given to every word in your document. So here is my vocabulary for this sentence. Just demonstration, rose red, text just, violet blue. Here we don't have individual words, we have bigrams, pairs of words at a time. And if we wish to see the corresponding numerical representation it has given, we just need to do a 2-dense function. So here is the matrix representation of this bigram. Here is the numerical representation of this bigram, and here's the numerical representation of next bigram. So in a way, we are moving step by step from just representing the words to representing not just the words, but also the information about their context or the position of their words or what words occur in the immediate neighborhood of the words. So next model, which is used pretty much is TF-IDF or term frequency and inverse document frequency model. It is a numerical representation, which is calculated as a product of 2 values, 2 metrics. First is term frequency, which essentially means how many times does the word occur in your document. And other is inverse document frequency, which tells us out of all the documents that are there in your text corpus, how many documents contain this word. So first we compute term frequency, which means how many times does this word occur in a given document. Then we compute inverse document frequency, which means, it is inverse of how many documents contain this word. If we go into the mathematical details of it, then inverse document frequency, which applies to a word, to a document, and to the corpus. Corpus means a set of many documents, let's say n documents, is the log of n. N is the number of documents in your corpus divided by count of how many documents in that corpus contain that word, the word whose IDF we are calculating. A product of IDF and term frequency is what we call as TF-IDF score of that word. Term frequency of a word is how many times the word occurs in that document. Simple. IDF is how many times, is the inverse of how many documents are there in your corpus which contain this word. So in a way, IDF is inversely proportional to the popularity of the word. More is the occurrence of a word in a corpus, less weightage IDF gives to it. So a very, very rare words will have a high IDF value. So we will be able to use these words as distinguishing characteristics or features of your text. This is very important when we are doing tasks like document categorization or identifying or doing topic modeling of a document. So here is how we can implement. Yes.
Professor, there is a question. Can document
Yes.
also be equated to a line in the DL?
Yes. Yes. A simple sentence can also be a document. Okay. A full file consisting of 1000 words can also be a document.
Thank you, Professor.
So this is how we use TF-IDF. We have it from sklearn's feature extraction module. We import the TF-IDF vectorizer class, define some text. we can very easily use the text from a data set. Like in the above demonstration, we use the data set of Corona NLP tweets. But just to keep it simple and to see what is happening, we are demonstrating it on very small text. So once you have defined your text, I call it document, you define the model TF-IDF, we specify the parameters to it like min-df, max-df, we spoke about this earlier. What is the minimum percentage of documents that should contain the word for the model to consider that word? What is the maximum percentage of documents that should contain that word in order to consider, in order for the model to consider that word? So then once you have created the model, we apply it to the document using fit transform function. It results in a matrix, which is the numerical representation of your document, of every word in your document. And here is what your matrix looks like. It has the representation corresponding to every single word in your document, right? I mean, we can't make much sense of it, but this representation can directly be fed to the classification models, classifiers like SVM or Naive or support vector machine, and you can apply tasks like sentiment analysis or document classification based on this representation of the text. Next, we are looking at the ways of converting text into words, which are actually used right now in real world. These are called word embeddings. Word embedding means, embedding is the technique of just creating a vector representation of text in the embedding space, in the space which represents all the words of your text. There are three prominent embeddings, word-to-vec, glove, and fast text. Now, all these embedding techniques use a neural network. They are unsupervised techniques. We feed a lot of text data to them, most commonly coming from web or repositories like Wikipedia and Common Crawler, or forums, blogs, publicly available data, libraries around the academics. So these are trained on a huge data corpus, and they learn the embedding. So they learn the vector representations of the words automatically. So word-to-vec, glove, and fast-text. Word-to-vector also uses a kind of bag of words model, which is called continuous bag of words model. It can take into account a long context. Instead of just having a look at bigrams or trigrams, 3 words at a time, it can look at longer sequences of words also and remember their context. So we will use word-to-vec model from Ginsem. It's a ready-made pre-learned representation of many English words, which is available to you by importing Ginsem. You can use it. So from Ginsem.models, we are loading word-to-vec. Again, we are defining some text for which we will find the encodings. You have to tokenize your text first, which we will do using NLTK's word tokenize function. And then we are building our model word-to-vec dot word-to-vec. This word-to-vec is your library, and this word-to-vec is the name of the class we are using to convert our text into a vector representation. We are passing it the tokenized corpus, which is the set of tokens of our text. We are specifying how many words should it look at a time. So 3 means it should look at trigrams, 3 words at a time, and the minimum count is 1, which means how many times the word needs to appear to be considered by the model. So 1, at least once your model, your word has to be there. And what kind of skip gram model we are using? So 1, skip gram is equal to 1 means we are looking at 1 word, 1 gram at a time. The model is taken in a variable called word-to-vector, and we can see the word, the vector corresponding to a single word. You can also see vectors corresponding to all the words in your text. So here we are looking at the representation or the corresponding embedding of word blue only. So this is what your vector looks like. This is what the corresponding numerical embedding of the word blue looks like. It has a size of 10, a size of 100. That is the average size of embedding for every word generated by word-to-vector model. You can also look at all the vectors. So here we have an array which shows us the representation of all the words in this text. So here we have very few words, I think 10 or 11 words, corresponding vector representations here. This very well can be applied to an entire data frame, to all the columns of the data frame. We have converted these vector representations into a data frame here. So here is the vector representation of word is. Here's the vector representation of dot, for the, for demonstration. So for all the words in my text, I have the corresponding vector which represents its vector representation generated by word-to-vec model. As we discussed, when we build an embedding, it should follow certain properties. For example, it should be able for us to compute the similarity between words. It should be able to identify morphological similarity in the words using this model. So that's exactly what we are determining here. For the words we have in our current document, can we compute cosine similarity? Cosine similarity is computed on vectors, right? It is the product of vectors divided by the modulus of those vectors. So for each word which is represented by a vector, we are computing its cosine similarity with all the rest of the words in the sentence. So you can see all the diagonal terms here are 1, which means the word is definitely and obviously the word is very similar to itself. And there is also the value of similarity with other words, the and as the similarity is like minus 0.5, minus 0.05, the similarity between this and this is something, the similarity between this and this is something, and so on. So the arithmetic operations which we normally do on words, the logical operations which we normally do on words is also possible to be applied to the corresponding vector encodings which are generated by word-to-vec model. We can visualize these embeddings in a vector space. So here are my 100 or 150 embeddings, and I can see where these words lie in this vector space, in this embedding space for all these words in my document, how close or how far away they are from each other according to the embedding we have generated in this particular model. So that is the TSNE model, which helps us in visualizing the vectors corresponding to words in a embedding space. We'll quickly look at the glove model. This glove model comes pre-bundled with Spacy. Once you decide to use glove embedding, you can download the large model of English from Spacy. A large model, why? Because the small sized and medium sized models, pre-trained models of English do not contain the vectors, do not contain the numerical representations of words, but large sized models do have. So in case you have not already downloaded the large pre-trained English pipeline, you can go ahead and execute this code. It will download and install this large pre-trained English model for you. Once it's done, you can create an object of it using the spacy.load function. Pass it the vocabulary, find out the vocabulary, which means the total number of unique words in your model. And then you have your own text, which you want to apply the embeddings on. For example, in this case, I have my document, which has some sentences, 3 English sentences. I tokenize my text using NLT case word tokenize function. You can see what vocabulary is there, which essentially means the unique words in your text. And then we apply NLP to our words. NLP is the pipeline we created of the English language pre-trained pipeline. It allows us to see the vector representations for every word. So NLP word dot vector, this vector function, this vector attribute allows you to access the ready-made or pre-trained vector embeddings which are available to you in Spacy library for every word in your current document. We convert these vectors into a data frame for ease of viewing. So here's your text, here is your representation for the word text, for the word is, for every word in your corpus or in every word of your document, you have the corresponding embedding. We can see that this is 300 long, which means every single word is represented by 300 numerical values in its vector embedding. Here we are looking at the vector embedding for the word violet. 300 numbers in a vector which represent the word violet. Here are the vectors for all the words, which are around 14 words in this sentence. And here we are visualizing, we are plotting in the embedding space all these words. You can see the words which occur very often together in this document and also in the pre-trained corpus. They are placed close to each other. Then the words which do not occur very frequently next to each other are placed far apart. The last model we'll be looking at here is fast text. Fast text is available in GenSim. Again, it is trained on publicly available internet data, and it has support for 157 languages, not just English. We need to import it from GenSim. The name of the pre-trained model is fast text. you need to have some text defined, or you need to have your text from a data frame or from a text file, or wherever you are accessing your text from, or maybe you're scraping it from a web page. Apply a tokenizer to it, tokenize your text, and then apply the fast text model to it. Pass it the tokenized text, specify how many words you want to look at in one go. The size of your window, or the window parameter, tells your model how many words at a time you want to focus on, you want to look at. Minimum number of words that minimum count that the word needs to be there to be included in the model. We are printing the embedding of word blue here. It is of 100 digits each, and then we can see that with shape parameter, you see there are 100 values in each vector corresponding to the word blue. Similarly, for every word, there will be a vector of length 100 representing that word in numerical form. You can see the vectors corresponding to all the words also like this. And then just like above, you can plot a TSCNE representation of vectors generated by fast text also. So this was a quick refresher of different techniques that we have for converting text to word. Whichever of these techniques is best suitable for you depends a lot on the data set you are working with. How many, what is the vocabulary of your data set like? What kind of corresponding model you are applying after this representation, which ML algorithm you are applying. That also determines what kind of pre-processing, what kind of representation you need to do, what kind of embedding you need to apply to your text. So I think I'm done here. Are there any questions?
Currently, we don't have questions. We have answered all the questions that has been asked by the attendees.
Yes.
And so thank you, Professor. It was quite an informative session on text pre-processing and representation, with giving examples and in-depth know-how with libraries that you have explained right now in the session. It was quite informative and quite useful to us. And
Yes.
to show the support, can you please show your thumbs up to the professor? Attendees, please show your thumbs up to the professor. Meanwhile, I would like to inform about the next session. It is going to be on next Thursday, and the session would concentrate on text classification modeling. So we are done.
And again, yes, again, it's going to be quite towards the coding side of it. So if there are any doubts regarding what to do and what not to do, you can reach out to me at any time, and we can sort them out before joining the session in where we are actually applying the models.
Yes,
so we'll be applying a specific pre-processing technique, we'll be applying a specific representation technique. And why we are applying that pre-processing technique and why we are applying that representation technique, that doubt, if if there are questions regarding that, you can reach out and ask anytime before the session also.
The session notebook could be shared before the session, and it will be useful for the attendees to get prepared with their questions. Yeah, thank you, Professor. Thank you for the session.
Thank you. Sure, I will increase the font size in the future session.